Okay, we are now recording. Um, okay, we are now recording, and we're gonna try chapters 23 and 24 today. We will try because we don't know if it's gonna fit in 1 hour. But let's try. So chapter 23 is about comonads, right? So just as a recap, which is of the important parts of monads, is that you have a function that lifts something. So you have something that does this thing, and you also have a function that allows you to pick something that is lifted multiple times and you shrink them. And we're going to make duals of those things today.
Yep.
So the dual of this function is going to be like this function, basically reversing the arrow. And the letters, right? Because why it's not WB to A. It's just about naming thing. It doesn't matter. And the fish operator analogous is this thing. So you have something that is already lifted. You have a function that picks something already lifted, returns you a peer a value, and then you have another function that picks the lifted version of this thing and returns you a pure C thing, and you want to compose them. You want to compose them. So this function, we're going to call it extract, which kind of makes sense. Which kind of makes sense.
Yep.
A lot of things are not comonads. So in some place he mentions the I/O. Yeah, I/O. This is, as far as I can tell, this is not actually true. You can unwrap the I/O, but that's GHC internal stuff. You can even pattern match the I/O, in fact, but it's not exposed in the for users because, well, you need to know pretty freaking good what the heck you're doing in order to have the to do that.
Yeah, it's like a GHC implementation detail. It's
Yeah,
needed for the compiler. They
yeah,
exposed it as a library because why would they not? But it's not for everybody.
yeah. You
Not for the
should,
faint of heart.
yeah, you should be very safe. You should know what the heck you're doing to do that. Cool. So this will be the comonad type class in Haskell. And then what are we going to use them in for programming, right? Uh, and then this is important. Some data structures provide a way to access their contents, but that's not always the case. This is just a bonus
Well, for monads, right? For
for monad.
comonads, you kind of need that.
Yeah, the comonad requirement is that. But there is a counterbalance, right? The comonad doesn't tell you how to wrap that again.
It doesn't. It really
It
doesn't.
allows you to peek inside it, but it doesn't allow you to lift it. So you are making a trade. You don't have lift, but you have peek. Um, so then we're going to go to the product comonad. So you can write the product like this, but there is the currying version, which is like this, and then you can make a type called prod, and this is already a functor, right? As we already know. And then you can define the comonad fish operator by doing this type of thing. So you have some. This is the same signature as before. Same signature as before. And what you're gonna do? You're gonna basically pattern match we're gonna return a function that picks a product. So we pattern match on that. We reconstruct that. Apply F. We're gonna get a B. Then you pick the same E as before. Make a product called G, and that's the return. The extract function basically just ignores the environment.
Yep.
Um, and what is inconvenient is that we don't have the notation for these type of things, as we do for monads. I would not be surprised if there is some sort of extension that, I don't know, how would you call that? Undo? Uh,
Uh, Odd.
that's
It's
cool.
an it's an odd notation
It's an odd notation.
because it's
Uh,
because it's do but backwards.
exactly. And then we're going to explore a little bit about the composition of the thing. So this is again the fish operation. The comonad fish symmetric version, let's say.
It's the coffee operator.
coffee.
because it's a cold fish.
Nah, that was terrible, dude. That was like beyond terrible. Jeez. Okay. So how can we produce a value? And here's some interesting questions. So we have this thing and a this thing. How can you produce a value of this type to use to fed G, right? What we have at our disposal is this thing, which is coming from this, and we also have the function f, which is this.
Yep.
So in order to, because before we did it in a specific case, right? We did in a specific case. We can in fact create, like lift up something to be a prod. That's why this question was unnecessary in this case. But in this case, it is. So then we're gonna make a function, an auxiliary function called extend, that picks the f, which is this, picks the thing that we also have, and somehow returns us this thing. We don't know how that's done yet, but this is what we're gonna assume it exists.
Can I say that just like bind versus join, I don't really like extend compared to the alternative that we'll see in a bit.
Wait, the alternative, you mean the duplicate?
Yes, duplicate.
Um, I don't think it's that easy in this case though, because as we are about to see, they are mutually recursive. So it's kind of tough. So
Okay.
assuming that you have extend on hand, you can implement this just like this. So if you have f, right? You have f. You pass it to extend, which is then turn. You're gonna get this thing, and then you can just pass that to g, which will give you the c that you want. So this will be the implementation, assuming that we have extend on hand. Um, and then the question becomes, what about the extend then? We just like swap the problem. We fix one and created another one by doing so. Uh, and then it comes a question. You don't have lift. That's the problem. Uh, but
We
then,
don't have lift.
but then, uh, it says the co-monad. No, at this point in the analogous construction of monads, we use fmap. The only way we could use fmap here is if we could have something of this type at our disposal. If we could only turn WA into WWA, so like the opposite of join. We're gonna call that duplicate. We're going to call that duplicate. And then you may ask yourself, wait a moment, we are creating another requirement. We may solve the extend implementation, but now
But
by doing that, we now have to implement duplicate, uh, which is fair, but that's like, I don't know how common it is in Haskell, but like in the traversable type class, you're going to see the same shit, which is that you have two definitions that they are mutually recursive with themselves, which means that given one, Haskell knows how to implement the other for you, which is very convenient, right? It's very convenient. However, you need to implement one of them.
yeah, you need to implement one. Yeah, if I was just implementing Command myself, not that I would do it very likely because I don't program in Haskell, so no type classes. But yeah, just like I prefer join, I would probably go for duplicate if I had to pick one to implement because I don't know, it just seems like a neater, just seems like a neater primitive in general.
Yeah, that's fair. But as you can see, duplicate uses extend and extend uses duplicate. So
Yeah,
that's,
you need to provide that. Those are the defaults, right? You need to provide one, and then Haskell can figure out the other.
yeah, which in my opinion is one of the gains of using type classes, because that means that you, just by doing duplicate, you gain extend for free. And in some cases, it's way easier to implement one in comparison to the other. So like you have no shit of idea on how to implement extend, but you know how to implement duplicate. So then that's it. Then you can just use extend. Um, so here are the intuitions behind those functions. A component can be thought of as of a container filled with values of type A. The product component is a special case. There is a notion of the current value, one that is easily accessible through extract, right? And the co-Classley arrow performs some computation that is focused on the current value, but it has access to all the surrounding values. We're gonna see another application of this shortly. And then it goes with the. This is a very neat way of implementing this shit because I thought about it, and I think this would be like a very good HVita alternative implementation.
Yeah, I thought of HVita immediately when they gave this example.
Yeah. So
Like,
so just for context for the recording, there is a thing that we did way like 2.5 years ago, the beginning of times, that we I implemented this thing, right? So at the time we wanted something very easy. Nathan wanted to do something in Haskell, so I implemented the game of life in Haskell, but I did it in a very naive way. The Chad way would do to do it like in this like what is describing here. And then
yeah,
we have the cells, and that's fine. And then what would duplicate do with the cells? It picks a container, so this thing, and produces another a container of containers, right? So a container of containers. And in Game of Life, you get a grid of grids. Each cell of the outer grid containing an inner grid that is focused on a different cell. Why would that happen? Because for each cell in your Game of Life board, you have the notion that for each individual member you have to figure out its neighbors. But the neighbors themselves could be living in an outer like lifted grid. So this is the intuition. And now we have the extend, which is that it applies a
mm,
computation to all of these A values, replacing them with B's. And the result is a common container filled with B's. So in the Game of Life, this would calculate the new state of the current cell. So you lift them to figure out their neighbors. And then you extend them by applying the neighbors algorithm thingy to identify what's going to be the next current thing. So this is very neat, dude. This is very neat. Not gonna lie.
yeah.
Uh,
Game of Life. It's very. It's just freaking booleans, man. Just freaking booleans.
well, if you're so triggered by that, we can swap the booleans with an ADT, whatever. It's the isomorphic. Who cares?
No, actually, I would prefer to use like because here's the thing: the reason you use booleans is because you implement the grid as an array, right? Which is very natural to do because well, it's literally a grid in memory, right?
Well, we didn't do it as an array. HVita uses a matrix.
Which is just a two-dimensional array,
I
like an
have no idea.
abstract,
You need to check the
like
package. I have no
no,
idea
no,
how they
no,
implement
no.
it.
I mean like an abstract array, not a concrete array
Ah,
necessarily.
okay, okay, okay. That's true then.
Um, but there's a slightly different way that you can implement this. You can implement this actually as a set of live cells.
But then to identify the neighbors, we do a bunch of lookups.
Yes, because each cell now is represented as a coordinate pair, you see? So the cell knows where it is.
Man, that definitely could be done. Definitely could be done. But I would be very no, not tempted, but it would be very interesting to try to implement the entire thing using extended duplicate. That would be very cool. Very cool. Uh, cool. Well, you know what this means though? I read
It's
this
just
and didn't understand.
it's foci. It's the plural of focus because Latin basically.
Yeah, so we first call duplicate. So like we had the grid of grids with the neighbors focused, and then we extend, applying the grid of grids to each individual one.
We have yeah we have map basically, which
Yeah,
is well
yeah, so cool. Then it comes the stream mode, which I never used. I actually need to be honest, I never used the streaming library in my life in any language. I never had to use those because at any time I could just assume, for instance, if you're reading a file, I never had to do this using the stream because I always had the memory to just read the entire
ah
file and that's it.
no, but uh, okay. Here's the thing. Have you ever done anything using standard I/O?
Yeah.
That's basically a pair of streams.
In which language though?
No, I mean abstractly. It's a pair of strings because you have the input, which is, well, an actual string that you are consuming, right? And then the output is a string that you are building, basically.
No, but what if I'm not building? I'm just reading the thing.
Then standard in is still a string. Like, here's the thing. In Haskell specifically, standard input is actually represented kind of like a list, right? Well, you have to use specific I/O functions to grab the contents and
No, but
prefixes of.
no, but in Haskell, actually, I don't know. In Haskell, is it a string just because it is I/O? I don't know how that works actually. The internal
No,
implementation.
it's because like when you grab stuff from standard in Haskell, you get a list of characters, right?
Yeah,
Usually.
yeah. Well, it can be other things, but sure.
But a list in Haskell can be infinite, right?
Well,
Because it's lazy.
no, yeah, but you should not do that. As far as I can tell, when you should use functions that read from a file and put them in a builder, because strings as list of chars they suck for performance.
Yeah, they basically bloat the number of bytes per character
Yeah,
essentially.
but if you're doing that, if you're doing creating a builder, which is like builder string or whatever the type is, how do you do that as a stream? As far as I can tell, you read the entire thing.
You don't have to because of laziness. But here's the thing: a builder. I actually don't know that particular API. Like Haskell is not really my specialty.
Builder Haskell. Yeah, this thing. Yeah, this thing.
Builders denote sequences of bytes. They are monoids. Okay. Uh, Internally, builders are buffer filling functions. They are executed by a driver that provides them an actual buffer to fill. Uh,
And by the way, if like just for recording purposes, I got to know this because of a book called Haskell in Depth. This book, which I have it. It's right here.
hmm, that's okay. That's nice. Okay, so you see that lazy byte string
Yeah. Oh, here.
type?
This thing.
Yeah, the lazy byte string. Uh, Abstractly, that's basically a stream, except it's specialized to only contain bytes.
Okay, but in that case, the fact that it's a stream is completely hidden from you. Like I used this before, but I never had to care like to notice that it is a stream instead.
Okay, here's a slightly more concrete example. You know the range function in Clojure.
Yeah.
I imagine there's another name, another function with a different name that does the same thing in Haskell as well,
Wait,
right? That
range
returns.
closure returns a lazy seq.
Yeah, if you
Oh,
call
this
it
this
with
is just yeah,
no.
but this is just the in Haskell it's like this, no? This.
Yes. Well, actually, it's zero dot dot because it includes
Sure.
zero.
Yeah, this thing.
Yes, that. If you do that, that's essentially a string, like because you happen to know that that particular string has no end technically, right? You can always grab the next step, the next value in the sequence.
Well, but in that case, any infinite data structure is also a stream.
Essentially, yes.
Sure, then. Okay, in that case, I did use streams, but I never had to care that they were streams, uh, which is cool, I guess. Anyway, so
Yeah, like
this is the string type, which is basically a list without the base case.
yeah, essentially.
So you do that. You can also fmap the thing. The extract is trivial. You just grab the head of it. Duplicate, you just cons. Uh, well, you
You
just.
cons the original list to the duplicate of the tail, basically.
Yeah, but that's.
In the case of a string, the focus is the head. So by looking at the tail, you are moving the focus, you see?
By moving the tail.
Yeah, because you see, the tail of the duplicated list is the duplicate of the original tail.
That's true.
And the tail is just a string where you are focusing on the element after the one that you got the tail from.
Yeah. No, but my confusion is because let's suppose that you have like a stream. So you have A, then AS. What are we duplicating here? Like, somewhere one element will be duplicated, right?
No, no, no. You're duplicating, like, okay, imagine you have the stream of natural numbers, 0, 1, 2, whatever,
Yes.
right?
Yes. Yes.
If you call duplicate, the result will be a stream of streams where the first stream is the natural number starting from 0, the one after is the natural number starting from 1, the one after
Oh, I
that,
see. No, I see. The stream starting from two and so on and so forth.
yes,
Okay, okay. So you're basically, I see. No, makes perfect sense. You're not duplicating an element. You're duplicating the entire thing.
yeah.
Makes sense. Okay, the first element. Oh, it's actually written here. Just forgot. The first element is original stream. The second element is exactly what Marinho said. So then you can implement for stream the component. Uh, and then you can also, and here's the thing, in an imperative language, this would be like a window, right? You would have
Basically.
some sort of thing that keeps track of the current one, and advance would shift the current one, which is we're gonna be doing by position usually. So then the analog of advance would be just this, which makes sense because this is also a stream. This is a stream. We're just advancing the current window. So that's nice.
Can I just say it's kind of nice that this version of tail and head, although head is called something else here, they cannot fail, unlike tail and head on normal lists.
Well, that's a catch in that because there is a way to make head and tail total, which is to use a non-empty list, which essentially is
Is
this.
what this is.
No, but there is a thing called non-empty. If you go to Google,
Oh, right. A non-empty is basically.
this thing,
Um, yeah, I've seen a definition like that somewhere else. It's basically like, yeah, it's a
this
different
type,
type.
yeah.
Yes, that one.
And
It's a pair.
it even has a different cons, like the
Yeah, it's
operator.
yeah, it's basically a pair of an element and a list. The list might be empty, but the element, well, is an element, right? So,
Yeah.
um, but here's the thing, though. That's a different type, right, from
Yeah,
a
it's a
normal
different
list.
type. This is not a normal list at all.
Yeah, non-empty and non-strict list type. Well, yes, because it's lazy, right?
Yeah, you don't need it to be strict. As this is also not strict.
Well, it can't be strict, otherwise you would fill up your
Yeah,
entire
it
memory.
would be fucked. Yeah, exactly.
Well, not necessarily. It depends on how you decide to represent the string, right? If you just represent it naively, well, actually, with this
Uh,
definition, it would in fact fill up your entire
yeah,
memory.
I think in this definition you wouldn't have a choice. Like I don't know which implementation detail that would not cause this specifically to not fill up your memory.
Uh, like um, one way to do that is if you happen to know the element type, like if you are specializing the stream already, you can exploit the structure of that type. Like for instance, if you have the stream of natural numbers, you actually don't need to materialize the entire stream. You can just hold the current natural number.
No, but would you call that strict then?
It is strict in the sense that you have a number materialized,
No, but you don't have a
and
string materialized. You're
well,
kind
I
of
guess that's
picking
fair.
arbitrarily that only part of it to be strict, which is fair. Like I'm not saying it's not fair. It's just that
No, but here's the thing. In that particular case, you don't actually have a tail. The tail is implied by the fact that you are iterating over natural numbers.
okay, so it's implied then. No, sure.
but then that's not really a general stream, so it's
Yeah,
also
yeah,
yeah.
it's kind of
It's a
cheated.
special case. Yeah, it's a special case, but like yeah.
Here's a
In
function.
general, you do have
Go
to
on.
fill up your memory,
Yeah,
unfortunately.
yeah. Well, assuming laziness by default anyway. Because I guess you could do this in like closure, but you're gonna have to do the reverse. Because in Haskell, you need to specify when things are strict. In other languages like closure, you need to specify where the things are lazy.
Uh, Clojure does have lazy lists, and in fact, all the list processing functions return lazy lists by
Yeah,
default,
yeah, map
which
v
can be
versus map. Right,
yeah, which can be annoying because it changes the input type, but well, that's life, I guess.
that's life. Okay, here's a sum s function. So you want to sum until you reach, like, you need to tell at which point it needs to stop because you cannot sum the stream. So that's how you do that. So you just recurse filling up the stream elements, assuming they are summable, right? Anyway. And then you can also have an average function, and then you can have a moving average. So you basically telling uh, how many elements you want to jump, I guess, to calculate the average. Is that? No, this is just doing that, but jumping the first one.
Moving average, extend, average n.
What is the type of extend again? Extend.
It takes a function, it takes a
It takes
common adjective
this
function and returns,
and the first element and returns up, well, the lifted version of the return of this thing. So what
yes,
are we doing here again? It's saying partially applied average n is a arrow, so you can extend it over the whole stream. We can extend it the whole stream. The result is the stream of running averages.
yes, because you say, okay, give me the average of the first n numbers, right? But then when you extend that, um, you're basically going to say, okay, give me all the moving averages over the first n numbers, starting from 0 and then 1 and then 2 and then 3, you
But
know?
what is a moving average or running average in this case? What is the semantics of that? What does that
Like,
mean?
that's the average of a window of recent values, basically.
Yeah, but what is the size of the window?
It's n, the arguments to, well, moving average and average as well.
Okay, so if I'm starting from the first one, this is the average from 0 to n. Then the next string will be from 1 to n.
Plus 1, actually.
1 plus 1 until n plus 1.
Yes.
Ah, I see.
You see, the
I see.
window that you are looking at, that's why it's called a moving window, because you have a fixed length window of elements,
Mhm,
and you
mhm,
are
mhm.
looking at the average of every possible window of that stream.
Makes sense. Makes sense. What is moving the window? Extend?
Extend, yes, because when you do
Mm,
that, you call duplicate, right? And
yes.
duplicate moves the window of the tail
Mhm,
when it
mhm.
nests the type.
Okay, okay. I think I see. This is definitely calculating the average given something of size n. That's fine. Uh, that is fine. Yeah, and then you're calling duplicate. Yeah, yeah, I see. I see. Makes sense. Okay, now call monad categorically. So you're basically grabbing the things that we use for the monad, which is from identity functor to the t, end of functor, and then from the t square going to t. So this is basically join, and this was return or peer. I actually prefer to say in pure terms. Uh, anyway, so then with the corresponding things would be the extract and duplicate things. So this would be duplicate, and this would be extract. And then there's a derivation of a monad from using adjunction. But the duality applies here, so the left adjoint becomes the right adjoint and vice versa. Since the composition this defines a monad this must define the comonad. So the co-unit will be this thing, right? And then my question becomes, are we going to put, because we need to reach this thing, are we going to put in the middle of this the identity, in the middle of this?
Uh, Yeah, we're basically just going to do a similar thing. Well, similar but different, right? Because it's backwards. We're going to exploit the fact that,
L
um,
composed with identity is L.
well, that as well, yes. But no, actually, it's because remember when we were looking at adjunctions and monads in terms of being the half of an adjunction?
I remember that.
This is looking at the other half, basically.
No, I noticed that, but it's saying to insert. We need to insert an R after L in the middle of this thing. And then I was asking
Yeah,
myself, how can we do that
yeah, you can. Yeah, you can exploit the fact that identity after R is the same as
as R?
R.
Yeah, so that's what I thought. So then you can gonna reach this, which basically goes to t square. Well, and then we got it, right? It's symmetrical, makes sense. And we also saw the monoid as a monad as a monoid, right? It was the previous chapter. Then at first glance, we use a comonoid, right? And then the sad part is the original definition of a monoid as a single object category doesn't do allows to anything interesting. When you reverse the direction of all endomorphisms, you get another monoid. Recall, however, that in our approach to a monad, we also used a more general definition of a monoid as an object of a monoidal category. The construction was based on these two things, which is basically the mapend and the mempty. The
Yep,
reverse of these morphisms produce a comonoid in a monoidal category. So we have something that goes to this and produces a pair, and we go from the thing to the unit. So this we're gonna have the split and destroy. Destroy is kind of like trivial; it's just const. And
yep,
split is basically, and then you're gonna have to define f and g. It's just a pair of functions. And then we need to identify what is f and what is g. So then we grab the monoid unit laws from the previous chapter. So this is where the lambda and the whole are coming from.
yep,
We do some uh, what's the name? Equational reasoning on this thing, and we discover that G is identity and F is also identity, which means that everything is a comonoid.
yeah. Everything is a comonoid.
uh,
Yeah, in functional programming, you have that everything is functions of immutable values. In object orientation, pure object orientation, you have everything is an object. In category theory, everything is a
it's a
comonoid.
comonoid. Yeah. Yeah, because they are kind of boring, right? You can always destroy them and you can always split them, like whatever. Uh, so the comonad is a comonoid in the category of endofunctors. And then we go to the store comonad, which apparently is the opposite of the state monad, which is interesting. Uh, so we're gonna use the same trick as before. We're using the adjunction.
Yep,
Uh,
adjunctions are fun.
so we're gonna do this. So we're gonna say that z is this thing. So we're gonna produce this is a function and this is the state. Translating this to Haskell, this is gonna be the data type. The co-unit of the adjunction taken as at the object A is the morphism. So um, basically what we saw before. So this, not that. Uh, where is it? Where
Co-unit
is the thing?
is
I think it's in the
co-unit
previous
is
chapter actually.
no co-unit is the well, I guess it would just be like F map of identity. No,
I think it was in the previous chapter. It's not in here, although there is another E, but it means something else in this context.
no risk of confusion.
No risk of confusion. In
Uh,
Haskell notation, which means that we have, I guess the state was a reader first, and then a product in the insides, and then it's the opposite. So now it's the product and the reader inside. This is our extract function. So again, what is that? Let's check the types. I think that's going to be easier for the everyone. What is the type of extract? You just uh, uh, here you have a thing lifted and you want to extract it out. So in the store, it's gonna be this thing. So you have a function that given an s produces a value. You just pattern match the thing and apply it. In the unit of the adjunction, so you have the value and you want to produce the thing. You want to produce the thing.
Yep.
Oh no, but this is the unit of state. This is
Yes.
co-unit. So this is the version for the comonad. This is the monad version.
Well, it
Uh,
is basically pure, right?
yeah, this is pure. This is pure. Can be rewritten as partially applied data constructor. The unit of the adjunction can be rewritten as partially applied data constructor. Wait.
Right, because this is a functor, not a bifunctor, right? And store takes two arguments.
Ah, I see. So you partial apply this. You just apply the. No. No, it is. So you have already the first thing partial applied. When the second comes, yeah, you can basically, this is basically pure. So to construct the other one or duplicate as the horizontal composition, you do this thing. So from this, you can derive this using the trick that we just said before, using the identity functor. And then you
Yep.
can plug this in. Uh, we're gonna get this thing as the implementation of duplicate. So you have this, you just wrap it around. Well, you actually pattern match in the store. You grab the function uh, that you have inside. You save it as the other store, and then you're gonna
Right,
get
because the
this
store
thing.
of f is a function as well, right?
The store of f is a function. The store of f. Uh, wait. Yes,
Yeah,
it is a
yeah,
function. It is a
yeah, it's
function.
basically unit. Basically unit.
Yeah, no, that's what we saw.
Yep.
It's basically unit. It is just confusing as fuck because if you partial apply this thing with the only the first guy, you know the type of this and this, but you don't know the type of that. However, if you do because of that, then that is why it is the unit when partially applied. And then this thing means that uh, you are partially applying only the internal one.
Yes, only the internal one.
Yeah, and then the duplicate. Yeah, yeah. Wait, but the duplicate needs to return a thing, not a function, right? Yeah, it needs to return you. So you have a store of A, and I want to return you a store of a store. A store of a
Which
store.
is what we have, in fact.
But the first element of the store. Oh, it's a function. Okay, no, it makes
I-
sense. So we are partially applying this thing because this is a function.
yes.
Yes. So here's a complete definition, which is what we just saw. Uh, so then we have an example. If s is an integer, reader int a is an infinite bidirectional. Well, let me read the beginning first because reader doesn't have an s. So you can think of a reader part of store as a generalized container of a's that are keyed using elements of type s. So this is basically a dictionary, which is cool.
Yes, you are taking a function and using it as a dictionary, essentially.
For instance, if s is an integer, reader ta int a is an infinite bidirectional stream of a's. Store pairs this container with a value of the key type. So reader int a is paired with an int. In this case, extract uses these integers to index into the infinite stream. Okay, and then there is a thing that is important to mention. I think this is not going to be performatic in comparison to like a dictionary that you see implemented in other languages. Uh, because usually dictionaries are using much fancier data structures.
But like
Probably this
functional
is
languages
not.
No, but functional languages are good at optimizing function like abstractions, right?
Well, but that's an implement. That's on the side of the compiler.
It is, yes.
If you just take this naively and you try to implement this yourself in a toy thing, this is not gonna go very well, I imagine.
Actually, it might because that's basically a closure, right?
That is basically a closure. But well, I'm not well versed into compiler implementation, so
Yeah,
I don't.
no, a closure is really just a pair of a function pointer and
Environment thingy.
yeah, the environment, which is usually just an array of all of the captured free variables.
Yeah, but is that more performatic than like a tree, like a B plus or B
It's
star,
literally
whatever they use for
it's
dictionaries?
literally just a function pointer, Lemus. It's code.
And that's not my problem. My problem is that how are we gonna do
Well,
the
the
lookups?
well the we are just going to call the function. So the performance actually depends on the implementation of the function of the particular f that you used to instantiate the store.
The particular f. So you're saying that this dictates the performance.
Yes, because that's a function, right? It's just code that you can execute given an input. So the performance of doing a lookup is just the performance of calling that function once with some arguments.
Uh, well, but we don't know the implementation of that in this example.
Yeah, we don't.
So it may suck. It may suck.
We can't, in fact, we can't know, right? Because it depends on how you decide to instantiate the store.
Well, we can't know. Yes, but the way that it is written here, it's kind of saying it as an example, right? So in this case, the reader entity is paired with int, and then the store uses the extract using the integer as an index, which is true. But I don't see how you're gonna make this performatic in Haskell without using any sort of unsafe stuff.
Levels, this is literally just a function that takes an integer and returns something else in the particular example that we were looking at.
Yes, yes. So how are we gonna like? I don't think you got my point. This is saying that we can use this as a dictionary, right? My question is how we're gonna use extract using the number as an index in an infinite stream. Cool. How performatic can? What about performance using this
It's
implementation?
it's literally just a function call, Lemus.
No, it's not, dude.
It is.
It
Look at the
isn't.
definition. It
No,
is. Look at the
the
definition of
definition is
extract.
saying that you're gonna grab an integer and return you the element, right?
Yeah.
How is that gonna be done? We just know the type signature of the function.
No, no, no. Look at the definition of extract for store.
Uh, it just does a function application.
Yes.
Just does a function application. Yeah, so that doesn't answer my question at all. Still, we don't know that. You were right before. You said we can't know it. This from this code that we have on right now on screen, there's no way to know it.
Yeah, the only way is okay, what's the particular f that we're using for this store?
And then I
That
said, what function could that be in
any
Haskell?
func
Any
any
function.
function.
Yeah, no,
It can
but
be any
you didn't listen to everything else, to the remaining of it. Which function? How can you make such a function that grabs an integer and returns you a thing that will not
Lemus, do you,
suck if you don't
Lemus, do
use
you
unsafe stuff?
Lemus, do you know how to make a function that takes an integer and returns something else?
Oh, yes, I know how to do that.
There you go.
Yeah, so then I don't understand at all. Because to me, it's saying extract uses this integer to index into the infinite stream. So we,
The string doesn't actually exist, Lemus. It's just implied by the fact that this function takes an integer as an input.
yeah, I don't think either I'm not understanding or you are not understanding my question, right? So let's suppose, I think I got it. So your function, it would be I see. So there's no, yeah, it's exactly what you said. There's no stream. This is just a, this function f is just a bunch of lookups. Like you can pattern match on all the possible integers, all the possible entries.
Yeah, you just have to realize the truth, Lemus. There is no spoon.
There is no spoon. I don't get the reference for that.
The matrix, the original one.
Ah, okay. So this, uh-huh, uh-huh. But then that sucks, right? Because how you populate the shit? You have to write it every time.
You populate it by defining your
The
function.
function. Yes, so
Yeah.
it sucks. Because if you want, like, ooh, I think this would be using some Haskell metaprogramming shit. Because let's suppose that you have the dictionary already, but it's not written in terms of a function. So let's use a very
Uh,
dumb example. You have a gigantic JSON that maps integers to strings.
that
To use
doesn't
this as the map,
that but that doesn't quite work, Lemus, because JSON dictionary is finite. The
and
function would be partial.
no, but if your key is an integer, the function will always be partial.
Not necessarily.
Aside of having a catch-all, you're gonna put a catch-all in there.
Dude, you know the.
I'm waiting. I know the.
Okay, okay, here's the thing. Suppose for a
Mhm.
moment that the function. Uh, let's suppose for a moment that A is just. Let's suppose that A is just a list, okay?
Sure.
A list of. I don't know, a list of integers, just to make things easy.
Okay. What is the key?
Well, the key is an integer because we didn't change that from the example, right?
Okay, so the
So,
key is an integer and this is a list. Cool.
okay, here's one very trivial example that covers every integer uh, and gives a different result for each integer in particular. You
Sure.
just take the input and you put it in a singleton list.
No, but that's a
That's a
very yeah, dude. But that's a
that's a
very tiny example that in which that works.
but it covers every integer.
No, it covers that, but that's not my example. My example was, what if I have a Haskell code that is already doing manipulations assuming I have a store? I already have this. Well, my functions, the API that I'm building, it is assuming the possession of a store. You can
Okay,
provide that as an argument, and I will do some manipulations for you. One of these manipulations can be a lookup. That's fine. But what if the data that you want to populate the store with, what if this is not going to, how are you going to do that manually? Because this is a function, as we already discussed.
yes.
And you were right. What if I don't have the function? What if I have data in another format?
Well, then you have to write a function that does a lookup on the dictionary that you have, right? Because that's the example. We have a JSON object that presumably we parsed it into a dictionary, right?
Yes.
Um, but here's the thing,
But how are you
because
going to
the
write a
dictionary, no,
function?
no, but because the dictionary is finite, if you just do a lookup, you get a maybe back, right? Because maybe the key is
Sure.
not in the input. You have to
Sure.
handle that case to define the function, otherwise it's not going to be well typed.
Yeah, but
Well, you can provide a default that covers everything, or you could call another function that you know is total over integers.
I'm kind of thinking I have a JSON thingy, whatever it is, and I want to create a store out of that. How would I do that? How would I do that? I think I would fold the JSON, grabbing the keys and the value pairs, and create a lambda that does that. And that lambda
Dude,
would be this thing. Because you don't have a lambda, right? You don't have a lambda. You only have an object. You have a whatever JSON something something.
but
How
an
would I be
object,
construct this thing out of that?
well, an object is a dictionary essentially,
Yeah,
right? You
yeah.
can call get on a with a fixed dictionary, and And that has almost the correct shape because it will be a maybe A instead of just an A, right?
Yeah.
You just have to handle the maybe, basically.
Yeah, so but then here's the thing. So yeah, I think I see. I would create a function. Yeah, we can talk about this later, but I think I know how to implement what you said. To create this lambda, because that's the key point of this. I would create another function that would spit this thing, and I would partially apply the JSON value to it,
Yes.
and that's it. Cool. And again, all of these parentheses was to talk how would you populate a store if you already have it. If you're not willing to write this function yourself, because sometimes it's like I don't know, a million entries.
Higher
Uh,
order functions to the rescue.
exactly. So duplicate creates a new infinite stream indexed by int. This stream contains streams as its elements. In particular, at the current position, it contains the original stream, as we already discussed before. But if you use some other int as the key, you would obtain a shifted stream positioning at the new index. Um and then you can convince yourself that if you extract on a duplicated store, you get the original one. The identity law for the component states that extract. Yeah, this needs makes sense. This actually makes sense. Uh, because if you duplicate it first, that means that you grab the original one in the first position of the stream, then you have other streams. The extract is picking the first one, so
Which
everything
is
else
the
goes to the
original
side,
one.
which is the original one.
Yeah.
The store component plays an important role in the theoretical basis of the lens library, which I'm sorry, I never played with lens. I read about it, but I never used them. And I know that they are used for nested records. Uh, so in particular, a function of this type. So you have an A and you create a store of that, and then you have a set and get functions, which is if you have a value at a particular field, I guess, and you want to set that value, and you also have the get. You need to pass the thing, and you get the other thing.
Yeah.
If A is a product type, set could be implemented setting the field of type S inside of A while returning the modified version of A. And similarly, get could be implemented to read the value of the S field from A. We'll explore these ideas more later, which we don't have time to because it's already 52 minutes. Thanks for my dumb questions, of course.
No, they're good questions. It's just, this kind of stuff is it's ridiculously general to the point where if you don't think through some examples to try to get the essence of the thing, like if you just stay in the abstract, it's kind of hard actually.
I think it's kind of the opposite. The abstract stuff is the essence, but
It is.
it's very
It
hard to
is.
talk about something in terms of its essence, so we use instances of it. Uh,
Yes, essentially. Essentially.
yeah, so it's kind of it's a complicated problem because as programmers, I think engineering in general, we try to be very generalists. So we try to understand the essence of something, and then we call the bridges between different domains isomorphisms. So if you have something in C and something in Haskell, and you find the common parts of it, and then you do the same for all other programming languages, you reach the essence of those things, which usually are some sort of lambda calculus or Turing machines. But
Combinatorial calculus as well.
but
Don't
then
forget that.
yeah, but then when we okay, we define the essence, but then later to talk about them, it's hard. So then we go back one level and go to the instances to talk about it. It's kind of funny. Uh, uh, and I guess it's because the essence of things, the things that live on this higher level of existence, they they are very their own
There,
nature being abstract makes it hard for us to imagine because this is just a bunch of letters. This is letters. This is letters. But the connections between the letters and their semantics, those you need to. It's hard for us to talk about them without examples.
yeah, they are too simple basically. Like The human mind is evolved and adapted to deal with complicated stuff, right? Because you need to be able to, well, primitive people needed to be able to hunt and gather and avoid predators, all that stuff, which is pretty complex.
Yeah.
But we're actually surprisingly bad at understanding simple things, like really simple things.
But I guess we need to define what means by simplicity in this case. Because if you're talking about moving parts, this is not simple at all. It takes you 23 chapters to reach this.
It's not about moving parts, it's about being divorced from any particular context, I guess.
But this is not divorced of any particular context. This is within a very specific context, which is category theory and adjunctions and all that stuff. If you don't know those, if the context is completely absent, these letters would not make sense at all.
I don't mean context in the sense of theoretical context. I mean context in the sense of concrete context.
Now, okay, then it makes sense. Then it makes sense. But I think it's a very interesting duality. We, as engineers, we love generalizing things and understanding like what doesn't change, like using Mageta's words. What is not changing among those things? Then we coin that as the essence of the thing. Everything else is isomorphic. But then, especially when you to reach there, we can't start by that, which is kind of funny because you would think naturally, like intuitively, that by starting by the essence, you have a better understanding because there's less fluff that you would ignore anyway. But then that's the funny part. The fluffiness, the extra stuff, is what allow us to reach the essence. But starting by that is hard. So uh, yeah, so it's kind of interesting thing, and I think that's the problem with that people have with category theory in general. That because a lot of the stuff is very theoretically, like in abstract terms and all that stuff, people have a hard time doing understanding it and judging its usefulness. And a lot of people say it's useless because they can't make an instance out of this. Uh, but I think that's a very dangerous path to say such a thing. Because how can you know something, the usefulness of something, if you don't know the thing? You need to know the thing. So
Yeah, it's all about knowing how to map the abstract to the concrete and vice versa, right? That's a very subtle skill.
no, but it's before that. How can you even attempt to make the mapping if you don't know the first?
That is true.
So, uh, well, that can go wild, but I'm gonna finish here because we just finished 1 hour. But I think that's important to keep in mind, especially if you read these type of books. Because like you may say, oh, the concrete part is Haskell. Yeah, but who is doing Haskell? Like Haskell is not more popular than Python, more popular than JavaScript. Is that maybe that it is part of the reason? It's because it requires. Well, this is not exclusive to Haskell necessarily, as we talked about. You can implement a lot of those things in other languages. But maybe one of the reasons that these approaches are not very popular is because of these requirements. You need to understand the abstract stuff in order to get the usability out of it. Um, well, at least in its fullness, right? Because you can do Haskell without knowing the categorical definition of a monad. You can do that.
You can.
I'm not saying by any means or stretch of the imagination that you need to understand CT in order to be productive in Haskell, but you're not going to get the full intuition because
Yeah,
this exists. You either refute this or you accept that this is correct. You can live without it. You can do programming and do useful programs, but this will still be
you
there.
you can even use it. You just won't be able to write it yourself, basically.
Yeah, or maybe justify it, right? You can use it and like take for granted using the packages, but you may not be able to understand how the conclusion came to be.
Yeah,
Uh,
you would
so,
be kind of lost, basically.
well, not necessarily because there are ways that you can explain things to people. that will not use the like quote unquote correct explanation, but it will be enough for your purposes. So the class the category thing, you could have kept that as an embellishment, and then you can have a bunch of examples explaining how that's useful, and never ever explain the categorical thing. However, if the person has is reaching a point in which that knowledge would be useful for the person would be incapable of identifying that because the person just doesn't know. So maybe the person is using monoids for 10 years, and on the 11th year, there is a problem that the person could not solve because she doesn't know the connections between a monoid and a monad.
You don't know the foundations, basically.
Um but well, that's just theoretical anyway. Assuming, well, theoretical that 10 years and then a problem came to be in the 11th. So that's possible, but I'm not. That doesn't necessarily apply to everything. Okay, I'm gonna stop the recording now.
Bye, future people.